this is how a pump system will look like. So you have a suction side on one side and discharge side on one side. On the suction side is where your water will be sucked into the pump, and the pump will increase the energy of the fluid and it will be discharged into your discharge line. So here is where we look at the Bernoulli equation. Now in the Bernoulli equation you will have, so you will do a Bernoulli equation between point A and point B. Point A is just before the liquid is going into the pump, and point B is just after the liquid is flowing from the pump. So this is what we call pressure at point A, PA over rho A plus G ZA over GC plus alpha A VA squared over 2GC plus, this is what we call as efficiency coefficient WP. This is the work term, is equal to PB over rho plus GCB over GC plus alpha B BB squared over 2GC plus HF. Okay, if you were to go look at the term by term in the Bernoulli equation, the first term is PA. PA is the pressure of the liquid at point A. Okay, so this is where PA is going to be. Over rho. Rho is the density of the liquid. G is the gravitational acceleration. ZA is the vertical height from the reservoir. GC here is the GC, we call it as GC, how do I say this? Just take for a while. You use GC to convert your unit. So in our case, it's not that important. Alpha is just a coefficient. VA is the velocity at point A. N is the efficiency term. WP is the work done by the pump. PB is the pressure at point B. Rho again is the density. ZB is the height of discharge. Alpha B is a coefficient again. VB is the velocity at point B, and HF is the total friction head. So I put here plus HF. So plus HF here means that it is a combination of suction side friction head and also discharge side friction head. Why I put it here? Because at the end of the, if you look at the previous slide, you want the total value of friction head will be suction friction plus your discharge friction head. So that's why we can put it here. So this is what we call the general Bernoulli equation for pump design. Why do we say general? Because of this GC term, this equation can be used for any units, any kind of units. Any kind of unit means here, it can be SI unit or it can be FPS units. So depending on which type of unit you want to use, you can use different value of GC here. So let's say if you want to use this equation in the SI units. So SI units means that you are using the values in kg, meter, seconds, those kind of units. Okay. So you can just ignore the value of GC here. For SI unit, GC value is 1. Okay. So that's why, since if let's say you are using for SI unit, so you can just say that the GC value is equal to 1. So if you substitute one value in all this term for GC, you'll get this equation. So this equation is solely for SI units. So in this equation, you can see that we have eliminated the GC term because GC is equal to 1. So again, this term, this equation is only valid for SI units. And we will be focusing our discussion on this equation. So your job is to make sure that you understand each and every term of this equation. What is PA? How do you find PA? What is ZA? How do you find ZA? What is VA? How you define your VA and how you calculate your VA? What is the value of efficiency? What is the value of farm work? And what is the value of all these terms? So again, this is the equation. So let's say this is just an example. If let's say the only friction occurring in the pump is accounted by the efficiency, okay, so if we already say that there is no friction in the pipe, there is no friction in the fitting, the only friction is happening is in the pump. So we can say that HF is equal to 0. Why we can say HF equal to 0? Because we are already accounting the friction of the pump in this efficiency term. So if let's say we assume that HF is equal to 0, then we can rearrange this equation to become like this. So what we do here is that we take all these terms from the left hand side and we bring it to the right hand side. So we have here is that efficiency times the work done by the pump is equal to PB over rho plus GZB plus alpha B VB squared over 2 minus everything from the left hand side, which is PA over rho plus GZA plus alpha A BS squared over 2. So why we need to know this? Because earlier we mentioned that total head, the equation for total head is equal to HT is equal to H discharge, the total discharge head minus the total suction head. So if you look at this equation, we can say that this term is the total discharge head, which is HD, and this term here is the total suction head, which is HS. So if we put here, so we can substitute the value efficiency times work done by the pump is equal to HD over HS. So we can say that HT is equal to efficiency times work done by the power. So if the problem is asking you to find the total head, so you can use this. So you need to find this value, efficiency times the work done by the pump. So this is one form of this equation. The second form is that you can rearrange the equation again. So you take the same terms and you put it together. So what I have done here, I have taken the pressure head term, I have put it together. I have taken the vertical distance head term, I put it together, and I have taken the velocity head term and I have put it together, so that it will be easier for you to calculate your total head. So this is up to you. Whatever way you want to calculate, either you want to use this equation, this form, this equation, or you want to use this form of equation or this form of equation. At the end of the day, you will get the same answer. So I would suggest whichever you are comfortable of using, because at the end of the day, you want to calculate this value. Most of the time, you want to calculate the value of total head. Okay, so remember earlier we mentioned that we want the unit of suction or discharge head or the total head will be in the unit of mass or unit of length. But if you look at the equation here, So again, this is the general term and this is the term for SI unit. So I'm just putting this to make sure that you are aware that there are two ways to write this equation. One in a general term, one in a SI unit term. So usually the suction and discharge heads has the dimension of work per unit mass or length squared per time squared. Now make sure you understand this properly. What does it mean by work per unit mass? So work usually have the unit of joule. Work has a unit of joule. So if you have, and then joule, you can define joule as kg per meter squared, kg meter squared per second squared. So if you have here work per unit mass, you'll get length squared per time squared. So all these terms, P over rho, okay, P over rho, G times Z, alpha V squared over 2, each and every term here has the unit of length squared per meter squared. Now if let's say we take an example, we know that V here is the velocity. Okay, V here is the velocity. Now velocity has the unit of meter per second. So if you times meter per second, you square the value, you'll get meter squared per second. So you can say that the unit here is meter squared per second squared, which is length squared per time squared. Now if you look at here, G is our gravitational acceleration and Z is the unit of length. So G, the unit for G is meter per second squared. And if you times meter per second times meter, you get meter squared per second squared. The same goes for your pressure. Pressure can be in terms of Pascal or ATM. So if you look at Pascal, so 1 Pascal is equal to 1 Newton per meter squared. So if you rearrange the whole thing, and then you know that your density has a unit of kg per meter cube. So if you do unit cancellation, again here you'll get meter squared per second squared. So that is why we can say that the suction head and discharge head has a unit of length squared per time squared. Now we want to make sure that our head is expressed in the unit of meters or feet of fluid, which is the unit of length. So to do this, we just multiply this equation by 1 over G. Okay, you multiply this equation by 1 over G, and then you multiply this equation with GC over G. Now again, this is just for your knowledge. This part of the equation is just for your knowledge. Please focus on this part of the equation. So in order for us to change the unit here from meter squared per second squared into meter only, we divide the whole every term here by G. So it becomes H over G, P over G rho plus Z plus A alpha V squared over 2G. Now if you check here, the easiest way to check here if the unit of H over G is meter or not, just look at the unit of Z here. Z is the vertical distance, and after you GZ divide by G, so you can just cancel off G, so you'll get here only Z, and the unit of Z is meter. So if the unit of Z here is meter, by right, the unit here must be meter, here must be meter, and the unit here must be meter. So this is how you convert your unit. Initially was meter squared per second squared into meter by dividing the whole term with the value of G. So that is how you get your suction and discharge rate in the unit of length. Now the second thing that we need to calculate is the power supplied to the pump. Power supplied to the pump, the term is PB. To any particular pump from an external force can be determined using PB is equal to M dot times WP. So M dot is the mass flow rate. Mass flow rate will have a unit of mass over time. For example, one of the unit for mass flow rate is kg per minute or kg per second or kg per hour, which is mass over time. WP is the work done by the pump, and the unit for PB will be watt. Okay, watt is also equal to joule per second. So you know that WP has a unit of work per mass. Okay, so work per mass is going to be joule per kg. So if you times joule per kg times kg per second, we'll get joule per second. And joule per second is going to be watt. So this is how you get the power supply to a pump. Okay, before we move on to this example, do you have any questions that you want to ask? So our first example here is benzene at 37.8 degrees Celsius is pumped through a system shown in figure 8.1 at the rate of 0.1515 meter per minute. The reservoir is at atmospheric pressure. The gauge pressure at the end of discharge line, okay, this is the discharge line, is 345 kilonewton per meter squared. The discharge is 3.048 meter and the pump suction is 1.22 meter above the line in the reservoir. The discharge line is 1.5 inch schedule 45. The friction in the suction line is known to be 3.45 and in the discharge line is 37.9. The mechanical efficiency of the pump is 0.6 or 60%, and the density of the benzene is 865 kg per meter cube. So calculate A, the developed pump head, B, the pump work, and C, the total power input. So the question is asking us to find three values, which are the pump head, pump work, and power input. So first of all, you have to be able to decide which equation that you want to use. So if you look at the question here, all the values in the equation are in SI units. So you can just ignore the GC value. Here GC value is equal to 1. Now, okay, before that, let's look at here. So here the condition is suction lift condition. So you have to find the values of all your terms in the Bernoulli equation. Now it says that PA here, the reservoir here is at atmospheric pressure. So you know that the PA here must be 101.325 kPa, kilopascal. So that is your PA. PB, where the discharge is happening. So PB is where you want to. Given here, the gauge pressure at the end of the discharge line is 345. Right? So it says here the gauge pressure. So if it's the gauge pressure, so in our equation, we have to use absolute pressure. So if you have gauge pressure, you have to add this value with the atmospheric pressure to get the absolute pressure. So that is the term for PB. Now it's saying that the discharge line is 3.048 above the level in the reservoir. So if you look at this figure here, this is your discharge head and this is the highest point in the reservoir. So you can say that this value here from above the level of reservoir to the discharge is going to be 3.048. So that is the value of this one. And then it's saying that the pump suction. So this is where the suction happens. It's 1.22 meter high from the level of the reservoir. So from this point to the center line of the pump, where the suction happens, the height is 1.22. So this is important for you to determine because you want to find the value of ZB and also ZA. The next thing the question give you is that you have the discharge line. This is the discharge line. The pipe that is used is 1.5 inch schedule 40 pipe. Okay, and then the friction, the suction line. So the suction line starts from here all the way until the pump. The friction line, the suction line has a friction of 3.45, and then the discharge line starts from this point all the way until your discharge point is 37.9. And then the mechanical efficiency of the pump is 60%. So those are all the information that you are given, and also the density is 865. So if you are able to identify all those information, by right you have no problems in solving this problem. So let's look at the solution. So the first thing that you want to solve is the upstream station A at the datum height. Okay, so we can see here at this point, the velocity can be assumed as 0. So VA prime is assumed as 0 because of the larger diameter of the tank in comparison with the pipe. So you must understand that we are using the Bernoulli equation between this point and this point. So let's look at this point first. So we know that at this point your PA is your atmospheric pressure, and then your VA here. VA here we say that the diameter of the reservoir. This diameter is so big as compared to the diameter of this pipe. We can say that even though there will be a velocity, but it is so small that we can assume it is 0. Why? Because this diameter is very big as compared to this diameter of the pipe. So that's why we can say that VA is equal to 0. So that is the first part of the question. Second part is we want to find VB. Now the only information we have for VB is that the pipe used is 1.5 inch schedule 40 pipe. So if you look at, I have shown you the appendix for a pipe schedule, right? So we know that the pipe used is 1.5 inch and the schedule is 40. Now if you look at this side of the table, you can see that the written here is capacity at 1 feet per second velocity. So if let's say you have a velocity of 1 feet per second, the amount of water, the flow rate of water that you can flow through the pipe is going to be 6.34. So this is how you read this table. So it's saying that for capacity of 1 feet per second, the velocity, you will have a flow rate of 6.34. Now in our question, it mentioned the flow rate of 0.1515. Right? So we already have the flow rate. Now using the information that we have, so I have changed 1 feet per second into 0.3048 meter per second. I have done the unit conversion here, and so that 6.34 is equal to 0.02424 meter cube per second. So by using these two values and our flow rate value, we can actually find the value of velocity at the discharge here. So at this point here, based on our value of flow rate and the information we get from the table, we can find that the value of flow rate at point B prime is 1.925. As for the value of alpha, we can assume that the value is 1 for turbulent flow. So now, going back to our original equation, we already said that this is SI unit, so we can just ignore the DC value, and then we know that VA is 0 and alpha is equal to 1. So we rearrange this equation and we get this kind of equation. We have eliminated the value of VA, and I also have eliminated the value of ZA. Why? Because if you look at our question here, this question is a question for suction lift condition. So in order for you to find your ZB minus ZA here, so if I were to go back to this figure here, so this is supposed to be your ZB, this is supposed to be your ZA. So remember, if the liquid is below the pump line, ZS is going to be negative. So this value is supposed to be negative value. In order for you to find ZB minus ZA, okay, the Z here we can see is ZD or ZD at the discharge, and this is Z as the suction. So ZD minus ZS is going to be, since this value is negative, so it's going to be ZD plus ZS. Okay, so that is how we get our total static heat. So total static heat is the highest point of the water discharge minus the highest point of the water in the suction side. Highest point of water discharge to the highest point of suction side. So in our case, highest point of water discharge to the highest point of water in the suction. So this value we already know to be 3.048. So that is why we don't need to calculate this value anymore, right? By right, if you look at the description given in that figure, you have to find the value of from this point, from the center line of the pipe to the highest point of discharge. So this is going to be your ZD minus your negative ZS. But in the question, it's already given to us. The discharge is 3.048 above the level in the reservoir. So from this point to the highest level in the reservoir. So that's why here we can eliminate the value of ZA because I'm already covering the value here in ZB. If you don't want to do like this, you are always more than welcome to find the value of this one first. Okay, how do you find this value? Just 3.048 minus 1.22. So you'll get a value here, and then you can assume that ZA has a value of negative 1.22, and the value of the discharge vertical distance here going to be 3.048 minus 1.22. If you plus those two values again, you'll get 3.048 meter. Okay, so that is why I have simplified our calculation so that we don't have a lot of things to calculate. Okay, so from here again, I've rearranged the equation. So now we have PB prime over rho plus GZB over GC, VB squared, B prime over 2GC plus HF minus PA over rho. So because two terms here are eliminated. Now GC is equal to 1 for SI unit, and then in order for us to get the value of heat in meter, so we multiply everything by 1 over G, and remember HF, this is the formula of HF. So HF is going to be on this pressure friction head on the suction side plus friction head on the discharge side over G rho. Why we are using this? Because if you look at the question, the value of friction is given in terms of pressure. So is similar to whatever we have here. So if you look at this term here, in order for us to convert it into meter, if you have pressure over density, you have to times with G here. So this is how our final equation will look like. So this is the term for pressure, this is the term for height, this is the term for velocity, this is the term for friction, and this is the term for pressure at the suction side. So once you get this equation, you can substitute all the values. Okay, so PB is your pressure at the discharge. Remember, it was given to us the gauge pressure, which was 345. Now if you want to find the absolute pressure, you just add in 101.3. So you'll get this is your absolute pressure. The G value is 9.81. Density value was given as 865 plus your total height 3.048 plus your velocity that was calculated squared times 2G plus this is the value of friction head on the suction side, and this is the value of friction head on the discharge side over your value of gravitational acceleration times your density minus the pressure head on the suction side. It was mentioned that the reservoir is at atmospheric pressure, so the value is going to be 101.325 over gravitational acceleration times your density, and then if you put this all in the calculator, you will get the value of 48.77 meter. So this is the value of your suction total heat, and the unit again is in meter. That is for question A. Now for question B. Question B is asking us to calculate the pump work. Now this is the initial equation, and we know that this whole term here is equal to 48.77, and we want to find the value of WP only, and we know that the value of efficiency is 60% or 0.6. So by rearranging the equation, WP is equal to 48.77 times your gravity, which is 9.81, divided by the value of efficiency, which is 0.6. So you will get WP is equal to 797.39 joule per kg. So this is the unit of your pump work, joule per kg. So that is for question B. For question C, it is asking us to calculate the value of total power input. The formula for that is PB is equal to m dot mass flow rate times your work done by the pump. So for our first thing to do is to calculate our value of m dot. How do we do that? Because we know that rho is equal to m over v. We know our value of rho, and we also know our value of volumetric flow rate. So we can do this, and 865 times 0.1515, this is value of Q, and since the value of Q was given in meter cube per minute, so we divide by 60 seconds in order for us to get the value of mass flow rate is 2.184 kg per second. Now why we need to divide by 60 minutes? Because at the end of the day, we want our unit to be in joule per second. Joule per second is equal to watt. Because if you don't divide by 60 minutes, you will get your mass flow rate will be in kg per meter. So if you divide the value of part, if you put all this value in this equation, this will have the unit of kg per minute, and this one will have unit of joule per kg. So if you do unit cancellation, kg per minute times joule per kg, you'll get joule per minute, and joule per minute is not watt. So that's why you have to change the unit here into kg per second. So that is how you get the value of PB is equal to 1741.5 watt. So that is how you solve for question C.